Watch this video in Lesson Reach. Pause and ask questions, take a quiz, or get help with assignments. Link below.
Usually when we talk about mathematics, there's this expectation of, absolute clarity. It's sort of like looking at a digital clock. You glance at it, it says 2 p.m., and there's no debate. It's just definitive.
Oh, for sure. We definitely prefer our numbers to be absolute. I mean, we want them to just hand us the answer without any, gray area at all.
But then you actually step into the real world. You're trying to figure out if that double discount at the grocery store is actually saving you money, or you're scaling a recipe, or maybe you're just reading a news article throwing out all these competing statistics.
Right, and suddenly that digital clock starts glitching.
Exactly. We find ourselves looking at this numerical landscape that is murky and honestly pretty intimidating to navigate.
It really is the mathematical equivalent of muddy waters. The clarity just completely vanishes when context gets messy.
Yeah, and rather than giving you the standard welcome preamble today, let's just dive straight into those muddy waters. On our desk for this deep dive is section 3.4 of chapter 3 from Contemporary Mathematics. And to make this as engaging as possible for you, we're going to formalize our dynamic a bit today.
I like where this is going.
Right. So I'll take on the role of the curious student, asking the questions you're probably yelling at your dashboard right now, and you can play the lecturer.
I will gladly put on the metaphorical tweed jacket for this. It's a good way to frame things. And as your lecturer, I want to start with a scenario straight from section 3.4 that highlights exactly why this stuff matters. Let's talk about college graduation rates.
Okay, lay it on me.
So suppose you read that public institutions have a 6-year graduation rate of 57.6%. Or if we represent that as a fraction, that is 72 over 125.
Which immediately is a fraction that feels really unsettling. Like 72 over 125 doesn't paint a quick picture in my head at all.
No, it really doesn't. Now let's compare that to private institutions. Their 6-year graduation rate is 65.4%. As a fraction, the textbook lists that as 377 over 500.
Okay, so if I'm just looking at the percentages, 57.6% versus 65.4%, it's a super clean comparison. The private institutions clearly have a higher rate.
Right.
But if a journalist or a study just hands me those fractions, 72 over 125 compared to 327 over 500, I have literally no intuitive sense of which is larger. My brain just stalls out.
Which is completely natural. Comparing fractions with different denominators is inherently confusing because you're comparing entirely different units of measurement.
It's like apples and oranges.
Exactly. It's like trying to compare the length of something measured in centimeters to something measured in inches without converting them into a shared language first. And this is exactly why understanding rational numbers, what they are and how they operate, is so crucial. It gives you the scaffolding to actually translate the world around you.
Well, let's start with that term then. What actually is a rational number? And as the designated student today, I'm going to ask that we skip the really basic definitions. Like, I know what a positive and negative whole number is.
Fair enough. The core definition is actually right in the name. A rational number contains the word ratio.
Oh, right.
Ratio.
Yeah, it is any number that can be expressed as a perfect ratio of two integers, a numerator, and a non-zero denominator. So the textbook uses classic examples, like a pizza cut into 8 slices where you take 3, that's 3/8.
Okay, I know I said skip the basics, but pizza always helps.
Right. Or, a group of 20 people where 5 are wearing hats, that's 5/20ths. It's just a clean ratio. But you're right, in the real world, you aren't always looking at fractions. Sometimes you're looking at decimals on a spreadsheet.
Right, decimals are everywhere. So how do they fit into this ratio definition?
Well, any terminating decimal is a rational number. Take 1.34, for example. It's rational because it literally means 134 over 100. It has a clean, definitive end.
Makes sense. But even decimals that repeat a pattern forever are rational. If you have 4.363636 going on infinitely, it's still a rational number because that infinite repetition can mathematically be reverse engineered into a perfect ratio of 2 whole numbers.
Okay, wait. So a rational number is basically a number that behaves predictably.
Okay.
Let me try an analogy here. It's like a story with a clear structure.
I like that. Go on.
It either neatly ends, like a terminating decimal, or it repeats a clear, predictable chorus forever, like a repeating decimal. It makes sense. But that immediately makes me wonder, what isn't a rational number? What's the exception?
The exception is the non-terminating, non-repeating decimals. Those are the irrational numbers. And to use your analogy, if rational numbers are predictable stories, irrational numbers are chaotic, unfinished rants. They just keep rambling on with zero predictable pattern.
That sounds exhausting. Give me an example of a chaotic rant number.
Well, a classic example is the square root of any number that isn't a perfect square. Like the square root of 25 is 5. That's clean, it's rational. But if you take the square root of 13, it doesn't divide cleanly.
It just gets messy.
Really messy. If you plug that into a calculator, you get 3.605551275, and it just goes on forever. No pattern at all. No ratio can perfectly capture it.
It just descends into chaos.
It really does. Today, if you aren't sure if a square root is going to give you a clean story or chaos, the textbook recommends using an online calculator, like Desmos. If it spits out a whole number, you have a perfect square. If it spits out chaos, you are dealing with an irrational number.
Okay, so we have these predictable ratios, these rational numbers, but the tricky thing about them, at least for me, is their shape-shifting nature. Like, a fraction can look completely different but represent the exact same value.
Yes, and recognizing when that happens is totally foundational. To quickly visualize equivalence, imagine a rectangle divided into 5 vertical columns, with 3 of those columns shaded in.
Yeah.
That represents 3/5.
Got it. 3 out of 5 columns.
But take that exact same rectangle, but draw 2 horizontal lines through it, cutting every original column into 3 smaller blocks.
So now I have a grid of 15 smaller blocks instead of 5 columns.
Exactly. And if you count the shaded blocks now, you have 9. So 3/5 and 9/15 occupy the exact same amount of physical space. They are equivalent fractions.
Wow, okay.
All we did was multiply both the top and the bottom of the original fraction by 3. We just divided the same space into smaller pieces.
Okay, visualizing the grid helps a lot. But practically speaking, I'm not going to sit in a meeting drawing shaded rectangles to figure out if 2 fractions are the same. How do we test for this algebraically?
We use the cross-multiplication rule, but rather than just throwing the algebraic formula at you, let's use the numbers we just talked about, 3/5 and 9/15.
Okay, I'm tracking.
To test if they are equivalent, you multiply diagonally across the equal sign. You take the top of the first fraction, the 3, and multiply it by the bottom of the second fraction, the 15. That gives you 45.
Right, 3 times 15 is 45.
Then you do the other diagonal. The bottom of the first fraction, 5, times the top of the second fraction, 9. That also gives you 45.
Oh, I see.
Because the two cross products match, you have mathematically proven the fractions are equivalent.
So top left times bottom right has to equal bottom left times top right.
That is the rule.
Yeah.
Algebraically, it's written as for fractions a over b and c over d, they are equivalent if a times d equals b times c. And the same logic is what allows us to simplify fractions too.
You mean like reducing them?
Exactly. You find the greatest common divisor to strip a bulky fraction down to its lowest term so it's easier to read. You can use the fraction button on a calculator like Desmos for that too.
Now, I have to push back here for a second. I'm going to lean hard into the student role.
Bring it on.
I have a smartphone in my pocket. If I want to know if 12 over 30 is the same as 14 over 35, I can just type 12 divided by 30 into my calculator app, and it says 0.4.
Sure.
Then I type 14 divided by 35, and it also says 0.4. Why on earth should I bother learning a manual cross-multiplication rule? Like, why do I need to know that A times D equals B times C when the machine can just give me the decimal?
It's a very valid question. And honestly, if the goal is just to quickly compare 2 constant numbers in your daily life, use the calculator. But learning the manual rule isn't just about getting the answer. It's about understanding the grammar of the math.
The grammar.
Yeah. Right now, you are dealing with constant numbers like 12 and 30. But in higher math, like algebra, those numbers are replaced by variables, x's and y's.
Ah, and a calculator can't give me a clean decimal if I type in x divided by y.
Precisely. When the numbers turn into letters, you can't rely on the calculator to bypass the structure. You have an equation where x over y equals z over w, and you need to solve for x. You have to know the structural rules of how fractions behave across an equal sign.
Okay, that actually makes a lot of sense.
Yeah, learning cross-multiplication with simple numbers builds the mental scaffolding you will absolutely need when things get abstract. You have to understand the machine, not just read the output.
I see the point. It's about building the foundational logic. And I assume that logic is exactly what we rely on when we start performing operations on these numbers. You know, adding, subtracting, multiplying, dividing.
That's exactly right. Understanding that fractions can change their form without changing their value is the key to all those operations.
Yeah.
Let's look at adding and subtracting first. You can't just add the top numbers together and the bottom numbers together.
Right, that never works.
No, you have to find a common denominator, specifically the least common multiple of the two bottom numbers.
So you shapeshift the fractions until their denominators match, and then you just add or subtract the top numbers, keeping that newly matched bottom number exactly the same.
Yes, exactly. Now, multiplication is a different story. You don't need a common denominator at all. You just multiply straight across. Numerators times numerators, denominators times denominators.
Okay, so as the student, I have to ask why. Why is there a fundamental difference in the rules there? Why does addition demand a common denominator while multiplication completely ignores it? That feels really contradictory.
It really does, until you think about what the operations actually represent in physical reality. Addition is about counting identical units.
Okay.
Think about pizza again. If I have one slice from a massive New York-style pizza, and you have one slice from a tiny personal pizza, we can't just add them up and say we have two slices and pretend we have the same amount of food. My slice is like 3 times the size of yours.
Right, that wouldn't be a fair split at all.
Exactly. To add them mathematically, we have to cut my slice into smaller pieces so that we are counting units of the exact same size. That is what finding a common denominator does. It forces us to establish a shared unit of measurement before we start counting.
Oh, wow. That makes perfect sense. You can't just pile up different sized bricks and call it a stable wall. You need the bricks to be uniform.
That's a great analogy, yes. But multiplication isn't about counting identical units. Multiplication is about scaling. When you multiply fractions, you are taking a fraction of a fraction.
So it's inherently changing the size.
Exactly. If you have half a pizza, and I want half of your half, I am inherently changing the size of the piece. I'm scaling it down. 1/2 times 1/2 gives me 1/4 of the original whole. Because multiplication is about changing the scale rather than piling things together, we don't need the pieces to be uniform to start with.
Okay, that clarifies multiplication perfectly, but division has always felt like a magic trick to me.
Oh, I know what you're going to say.
Right. The rule we all memorized in school is to take the second fraction, flip it upside down to find the reciprocal, and then change it to multiplication. I know what the rule is, but why does flipping a fraction upside down magically achieve division?
That is the best question to ask. To understand why flipping and multiplying works, you have to think about what division is actually asking. Division asks, how many of these fit into that?
Okay.
Let's say you want to divide the number 10 by 1/2. You are asking, how many halves fit into 10 wholes?
Well, there are 2 halves in every hole, so if I have 10 holes, that would be 20 halves.
Exactly. The answer is 20. But look at the math you just did intuitively. You knew there were 2 halves per hole, so you multiplied 10 by 2. Dividing by 1/2 is mathematically identical to multiplying by 2 over 1.
Wait, really? It's just that simple?
It really is. When you flip a fraction, you are essentially finding its inverse scale. Division is just scaling by the inverse. So instead of trying to figure out how to divide by a fraction, we just flip it to find the inverse, and then use the straightforward scaling rules of multiplication.
And obviously, order of operations still applies to all this, right? The whole PEMDAS thing.
Oh, absolutely. Parentheses, exponents, multiplication and division, addition and subtraction. That applies to fractions just as strictly as it does to integers.
It's all connected. It's not just arbitrary rules to memorize. It's a deeply logical system. And speaking of that logic, the textbook uses these operations to point out a really mind-bending property of rational numbers, the density property.
Ah, yes. This is where the math starts to border on philosophy. The density property states that between any 2 rational numbers, there is always another rational number.
Always. Like, no matter how infinitesimally close they are on a number line.
Always.
Yeah.
And we can prove it using the operations we just discussed. If you want to find a number between any 2 fractions, you just add them together and then divide the result by 2.
You're just finding the average.
Exactly. You're calculating the exact average, finding the midway point. Since adding fractions creates a fraction and dividing by 2 creates a fraction, the midway point is always a new rational number.
Let me try a metaphor here. If you think about a digital photograph, you can zoom in on a detail, but eventually the image pixelates, right?
Right.
You hit a single square of color and you can't zoom in any further. There is a smallest possible unit of the image. But with rational numbers, what you're saying is that the number line never pixelates.
Never.
If I zoom in between 1/4 and 1/5, I can always find a new fraction. And then I can zoom in between that new fraction and 1/4 and split the difference again. It never hits the smallest possible fraction.
That is a phenomenal way to visualize it.
Yeah.
Yes, the number line of rational numbers has no minimum resolution. It never pixelates. You can divide the space, infinitely.
It's a heavy concept to wrap your head around. It's literally infinity hiding in plain sight between 0 and 1. But obviously, fractions aren't confined to just the space between 0 and 1. We deal with numbers larger than a single whole all the time.
We do. And that brings us to mixed numbers and improper fractions. A mixed number is just an integer combined with a proper fraction. If you have one whole pizza left over, plus 11 slices of a 12-slice pizza, you have 1 and 11 twelfths pizzas.
But mathematically, keeping it as a mixed number can be really clunky when you're trying to perform operations.
Right. It's usually much easier to work with it as an improper fraction, where the numerator is simply larger than the denominator. You just consolidate it all into slices.
How do we do that again?
To convert 1 and 11 twelfths, you just ask yourself, how many twelfths are in that one whole pizza? The answer is 12. Add those 12 to the 11 you already have, and you get 23. Your improper fraction is 23 over 12.
It's just converting wholes back into parts so the math flows easier. But speaking of practical, let's take everything we've talked about, the shape-shifting, the scaling, the fractions, and bring it down from the infinite abstract to the grocery store aisle. I want to talk about real-world power, percentages, and unit conversions.
Oh, this is where understanding the machinery of fractions pays off every single day. Let's start with percentages. The word percent literally translates to per 100.
Percent, right.
So any percentage is really just a fraction with a denominator of 100. If we want to find a percentage of a total, the formula is straightforward, the percentage over 100, multiplied by the total.
Let's use the real-world shopping example from section 3.4, the Wegmans cereal markup.
It's a great example of retail strategy. So suppose a grocery store buys a box of cereal from the distributor for $1.50. They put it on the shelf and sell it to you for $2.29.
Okay, so they raise the price.
Right. The markup, the flat amount of money they added to the price is 79 cents. To figure out what percentage markup that represents, we take the part, which is 79 cents, and divide it by the original whole, which is $1.50.
Got it.
When you multiply that by 100 to make it a percentage, it comes out to roughly a 52.6% markup.
Which is a pretty standard retail calculation. But here is where retailers really play games with our intuitive understanding of math, the repeated discount trap.
Oh, this one gets everybody.
I see this at clothing stores constantly. You find a jacket marked $150. The rack has a sign saying everything is 50% off. But you also have a loyalty coupon on your phone for an additional 25% off all sale items.
And your brain immediately does simple addition.
Exactly. 50 plus 25 is 75. I'm thinking, I'm getting 75% off this jacket.
And that assumption is exactly what the marketing department is banking on. But the math of sequential discounts tells a very different story. The discounts do not happen simultaneously. They happen one after the other.
Walk me through the actual math. Let's expose the trick.
The original price is $150. The first discount of 50% applies to that initial whole. Half of 150 is 75. So your sale price is $75.
Okay. Still feeling good about the deal so far.
Here's where the trap springs. Your additional 25% off coupon does not apply to the original $150. It applies to the new, smaller whole of $75.
Ah, because multiplication is scaling and the scale has changed.
Exactly. 25% of $75 is only $18.75. If you subtract that from the $75 sale price, you end up paying $56.25 at the register.
Let's do the autopsy on that then. If I paid $56.25 on a $150 jacket, my total savings was $93.75.
Right.
To find my actual percentage discount, I divide my savings, 93.75, by the original whole of 150. That gives me 0.625. I got a 62.5% discount, not 75%.
Exactly. It's a 62.5% total discount. Because that second 25% discount was a fraction of a much smaller whole, it didn't hold the same weight as it would have on the original price.
That is sneaky.
It is. This is why understanding that fractions and percentages are entirely dependent on the whole they are attached to is so vital. It literally protects your wallet.
That is genuinely eliminating. Okay, let's look at another area where my intuition usually completely fails me: unit conversions. I am terrible at this.
You are definitely not alone there.
If a recipe is in metric or I'm trying to figure out gas mileage in another country, I always just freeze up.
Unit conversions are basically just multiplying fractions. But the trick is to use the units themselves, the words like liters or gallons, as part of the algebra. Let's use the textbook's example. You have 14 liters of water. and you need to know how many gallons that is.
Okay.
The conversion rate is that 1 liter is equal to 0.264172 gallons.
So here is my student dilemma. I have 14 and I have 0.264172. Do I multiply them or do I divide 14 by that number? It always feels like a coin toss in my head.
You don't need to guess, and you don't need to memorize whether to multiply or divide. You just set it up as a fraction and let the units act like variables that can be canceled out.
How does that work?
You start with what you have 14 liters over 1.
Okay, so 14 liters is on top.
Now, you are going to multiply this by a conversion fraction. The golden rule is that you want the unit you are trying to get rid of to end up on the bottom of this new fraction, so it cancels out with the top of the first fraction.
Okay, I'm following.
Since liters is on the top of your first fraction, you put 1 liter on the bottom of the conversion fraction. That means the 0.264172 gallons has to go on the top.
Oh, so because liters is on top of the first fraction and on the bottom of the second fraction, they just cancel each other out exactly like reducing numbers and cross multiplication.
You got it.
I'm left with only the word gallons on top. And because the conversion decimal also ended up on the top, the structure naturally dictates that I multiply 14 by the decimal.
Precisely. If you had started with gallons and wanted liters, you would have had to put gallons on the bottom of the conversion fraction to cancel it out. That would have put the decimal number on the bottom, mathematically telling you that you need to divide.
That is brilliant. The fraction structure basically does the thinking for you. You just align the units so they cancel out.
It's an incredibly useful framework.
Well, we've covered a whole lot of ground today, navigating from the chaotic rants of irrational numbers to the elegant logic of equivalent fractions. We unpacked why division is just inverse scaling, and we armed ourselves against retail tricks and conversion confusion.
It's a lot of tools added to the toolkit for sure. But before we wrap up, I want to leave you with one final, slightly provocative thought. It brings us back to that density property we discussed earlier.
The idea that the number line never pixelates.
Exactly. Mathematically, it is an absolute certainty that you can endlessly find a new fraction between any two fractions. You can divide infinity forever. But what happens when that pure infinite mathematics crashes into physical reality?
Wait, what do you mean?
Well, Section 3.4 brings up a real-world application of mixing fractions of topsoil, peat moss, and compost for a garden. Mathematically, according to the density property, you can take a cup of that topsoil and divide it in half, and divide that half in half again, infinitely.
Right. The math says you can continue having the soil forever.
But in the real world, you obviously can't.
Well,
Right. In the physical universe, eventually you hit a single grain of dirt. If you manage to split that, you hit molecules. Split those, you hit atoms. Eventually, you reach the realm of quantum mechanics and the Planck length, where space and matter might actually be quantized.
meaning they do pixelate. There is a physical limit to how small things can get.
Exactly. The mathematics of rational numbers provides a perfect, flawless map. But it is vital to remember that the map is not the territory. Math is a conceptual framework for understanding the world. But the physical world has its own boundary lines.
That's wild to think about.
It is. It's something for you to ponder the next time you're trying to have a recipe in your kitchen. Where does the absolute certainty of mass end and the pixelated reality of physics begin?
That is definitely something to chew on. Thanks for playing lecturer today and guiding us through this.
Anytime. It was a pleasure.
And to you listening, as you go out into the world today, whether you are battling a confusing sale rack or trying to scale a tricky ratio, remember that the numbers don't have to be intimidating. They might not be as simple as a digital clock, but once you understand the machinery and the logic behind them, you can navigate the muddy waters. Keep diving deep.